I guess my question is, would we see a case for heating by the fin instead of cooling by the fin?
Oh, okay. Oh, okay, got you. So what if the TF is larger than the TW, right?
Yes.
Yeah, I mean, because remember, as I explained here, let's have a look at this governing equation. Okay, so remember this equation that we derived, right? This one, minus d over dx, this one, right? We said that it doesn't matter whether the T is large or TF is large. You get exactly the same equation, right? But the profile is just going to be different just because your theta, I mean, the theta is going to have the same profile. But once you actually solve for T, you might have a different T profile, right? Because like, imagine you have this theta. And depending on what is your TF and TW, you can actually get different T values, correct? Does that make sense? And the equation would not change. This equation would be the same, by the way. This equation would be the same. This equation would be the same. All these equations would be the same. But depending on whether TF is larger or TW is larger, you might get the T less than TF or larger than TF. Okay?
Okay, I got it. Thank you.
No problem. Because here I said that we didn't actually make the assumption that the Tx is larger, but what we did is basically, if Tx is larger, Tx minus Tf is a positive number, so this corresponds to the heat lost, so I should actually put a negative sign here, right? But I said if Tx is smaller, then let me write it as Tf minus Tx, right? So that this becomes positive, but it would be an input to the system. You would get a positive, but this thing and this thing are exactly the same thing, right? Because you can actually change the order of TF and TX and make this minus instead of plus. Does that make sense?
Yes.
So it doesn't change your formula. You get the same governing equation, but you might actually come up with different Tx values depending on what your Tf and Tw is. Okay, cool. Okay, good. Any other questions? No? Okay. So today I want to talk about two-dimensional steady-state heat transfer. Two-dimensional steady-state heat transfer. We're going to learn a lot of mathematics here, or maybe we're just going to remind ourselves of our mathematical background on how to solve differential equations. It's going to be highly math involved. So that I just set up the expectations and okay. And so let's talk about what our system looks like and what do we mean when we say two-dimensional steady state. Imagine you have a plate, okay, a two-dimensional plate, and we can actually neglect what's going on deep inside. And this is my x-axis, this is my y-axis, and I can call this z-axis. Well, actually, if x and y is the z-axis, is going to be the other way around, right? From the right-hand rule. X, y, z, yeah. Okay, that's the z-axis. But I assume T, temperature, on the plate is a function of x and y only. And T is not a function of z. That means that the temperature here is the same as temperature here and the same as temperature here. But the temperature here is not the same as temperature. If you go along the x or y direction, the temperature is not necessarily the same. But if you go deep into z direction, then the temperature does not change. Okay, that's my two-dimensional system. Okay, and let me give you the dimensions. This is A. This is B. And this phase is kept at T0. This phase is kept at T0. This phase is kept at T0. And this phase is kept at, let's make like some variation and assume that T at any x, but at y is equal to B, is equal to some function of fx. Imagine that I know the temperature variation here. Okay. You might have a heating element here, you might be heating it, but you can actually keep it at a constant temperature, but the temperature might be changing along this direction. Okay. Let's say this is any given function. Okay. And I want to find out the temperature profile T as a function of x and y, the given boundary conditions. And I'm sorry. Here's what we're going to do. We're going to do shell balance again, but this is going to be a two-dimensional shell balance. So I'm going to explain what I mean in a second. So I'm going to take a small shell. Okay. With a dimensions delta x, delta y. You can actually have it also along the z direction, if you like. Delta z. Okay, so I got a cube there. My shell looks like this. Okay, delta x, delta y, delta z, and imagine that the heat flux is entering like this and exiting like this. So it's entering both the like on the face which is perpendicular to the delta x-axis, also the face which is perpendicular to the delta y-axis or the y-axis. Okay. Okay. So if you do the shell balance, as we always do, in minus out plus generation is equal to accumulation. And it's at steady state. I'm just keeping these temperatures constant, T0s and this. And I want to see how the temperature is going to look like after a while, after the system gets steady state. So this is 0 due to steady state. There's no generation. You might actually come up with interesting problems by imposing heat generation with like generation rate, fancy R that times the volume of the shell. But let's keep it very simple, because even with this simple case, the math involved is going to be complicated. So let's try to solve this one first. So whatever comes in is basically the Q, the heat flux, along the x direction, right? So I can actually simplify my picture by decomposing the heat fluxes into x and y components. This is my qx. This is my qy. This is my qy at y plus delta y. And this is my qx at x plus delta x. So I decomposed the components of this vector into x and y components, right? So that I made it easier picture or simpler picture of the whatever is getting in, whatever is getting out. So I have 2 inputs and 2 outputs. And whatever is coming in is qx at x times delta z times delta y, correct? And I want to calculate it at x equal to x. Another whatever comes in, you can either like add all the ins minus add all the outs, or you can just do all the ins towards the, all the ins and outs towards the x direction, and then all the ins and outs towards the y direction. I'm going to do the latter. So minus whatever comes out along the x direction is qx delta z delta y at x plus delta x, plus whatever comes in along the y direction is qy delta z delta x this time, because this area has delta x and delta z, right? Estimated at y minus whatever is coming out is this one. That's qy delta z delta x estimated at y plus delta y. And that's all my ins and outs. That's equal to 0 because I don't have any generation, I don't have any accumulation. So that's the equation. But we need to convert it into differential equation to be able to solve. And the idea is to divide the equation to delta x times delta y times delta z. Okay, and take the limit as delta x goes to 0 and delta y goes to 0. Okay, and if you divide this equation into delta x, delta y, delta z, then the delta z's are going to cancel, right? For this part, delta y's are going to cancel, but there's going to be a delta x surviving in the denominator. So you get qx at x minus qx at x plus delta x divided by delta x, limit as delta x goes to 0, plus for this part, you get rid of the delta x, but the delta y appears in the denominator. So you get qy at y minus q along the y direction at y plus delta y divided by delta y. And this is when delta y goes to 0. and the sum is equal to 0. Correct? Okay, good. And the first term is the negative derivative along the x direction of the flux. So that's minus dq x over dx. Okay. But I should actually show it in partial derivatives. So instead of d over t, it's going to be del over del qx over del x. Del corresponds to the partial derivative, meaning that you're keeping the y constant while changing dx. Similarly, the second term is minus del qy over del y is equal to 0, right? Now, Fick's law, we need, Fourier's law. We need the Fourier's law to get an equation for temperature. Okay. So we need the Qx is equal to minus K del T over del X in Cartesian coordinates, right? And Qy is equal to minus K del T over del Y. This is in Cartesian coordinates for isotropic materials. What does isotropic means? It means the conductivity along the x direction, kx, is equal to the conductivity along the y direction, and that's also equal to the conductivity along the z direction. That's equal to k. Okay. So that's why I use k here, and I use the same k here. Okay. Some materials have different heat conductivities along different directions. One example is, for example, beef. If you cook the beef in different directions, it's going to have a different heat conductivity, and it's going to actually cook in a different amount of time, depending on which direction are the leans are aligned. The muscle skin, I guess, is aligned. So there are materials, really, in reality, that you have different heat conductivities along different directions. But for most of the materials, we can assume that it's isotropic, like, for example, uniform metals, like alloys generally, which doesn't have any molecular level directional inhomogeneities, which doesn't have inhomogeneities, like, for example, metal, like aluminum, copper, and so on. Okay. So far, so good. So we're going to plug in these equations. Okay. And we get minus minus makes plus, k del square t over del x squared. That's going to be the second derivative, plus k del square t over del y squared is equal to 0. And from here, after simplification, you get rid of the k's, and you get del square t over del x squared plus del squared t over del y squared is equal to 0. That's your governing differential equation. Okay. So that's one step. That's the first step to solve. That's the most important part of this problem, to actually come up with a governing differential equation. Okay. Any questions so far? Yeah. Okay. Now let's make a page 2. Okay. Now we got del squared t over del x squared plus del squared t over del y squared is equal to 0. And to be able to solve a differential equation, I need to also declare my boundary conditions with the boundary condition 1, which is x is equal to 0, x is equal to a. This is y is equal to 0. Let's call this y is equal to b. Okay. And we know that this phase is t0, meaning that at y is equal to 0, no matter what x is, t is equal to t0. At x is equal to, I'm sorry, y is equal to 0, t x comma 0 is equal to t0. Now you don't need to write this because I already write the y is equal to 0 here, so you can actually get rid of this. Okay. And the second boundary condition is this surface being t0, which is at x is equal to 0, t0 comma for any y, 0 comma y is equal to t0. And then this surface is also t0. That means boundary condition 3, t at x is equal to a comma any y is equal to t0. And the fourth boundary condition is this surface is at a temperature f of x, which you can actually provide. So t at x, any x, but y is equal to b is equal to f of x. There you go. So the system of equations to solve is this. Okay, I need to solve this set of equations. Do you remember any technique that you know or learned from analytical methods, for example, or any math course that you can apply to solve this second order partial differential equation? Any idea? Yeah.
Separation of variables?
Exactly. No? Exactly. So we're going to use the separation of variables. Okay. But before that, I just want to do one more thing to the equation. I'm going to change the variables. You can either like non-dimensionalize your equation, right? But I only have one value of temperature here. So you can use, for example, theta is equal to T over T0, right? And that's going to make your boundary condition like 1 instead of T0 here, which is going to be a known value. That's one of the good things about non-dimensionalization. You can actually make simpler boundary conditions so that your solution is more general. But you can also make it 0 by saying theta is equal to t over t0 minus 1. Okay. And but when you non-dimensionalize the x's, it might get a little messy, because for the x, if you use psi x over L, and another variable, maybe phi, is equal to y over L, but this time for x, the L is A, and for y, it ranges from 0 to B, using like two different characteristic lengths actually might be problematic. So instead of non-dimensionalizing, just let's forget about the non-dimensionalization, and just let's simplify the boundary condition by just simply subtracting the T0 from the temperatures. Okay. So we call this change of variables. First, let's define theta is equal to T minus T0, so that my boundary condition is going to be simpler, like 0, a number that I can work easier with. And your equation is going to be, with this change of variables, your equation is going to be, again, del square theta over del x squared plus del square theta over del y squared, because the derivative of a constant number is 0. It doesn't appear in this equation, 0, but in the boundary conditions, we get simpler equations. T, or theta, this time theta, at x comma 0 is equal to 0. Boundary condition 2, theta 0 comma y is equal to 0. Boundary condition 3, theta a comma y is equal to 0. And the boundary condition 4, theta x comma b is equal to f of x minus t0. Okay. So I have this governing equation and these boundary conditions instead. Simpler ones. Any questions so far? Okay, so let's do the separation of variable now. We're going to assume that the solution theta, which is a function of x and y, can be written as a product of functions, one of which is a function of x, the other is a function of y. Okay, that's the separation of variables. We are going to plug into the governing differential equation to see how, like, what information we can get out of this that defines the f of x and g of y separately. So plug in this theta xy into the governing differential equation to find del square over del x squared of theta, which is f of x g of y, plus del square over del y squared f of x g of y is equal to 0. I did nothing but wrote down this equation and plugged in the value of the theta. So from here, this g of y does not change with x, so it can be taken out of the partial derivative with respect to x. Similarly, f of x is a function of x only, so you can take it out of the double partial derivative with respect to y. So you get g of phi del square f of x divided by del square del x squared plus f of x del square g of phi over del y squared is equal to 0. Right? And you can divide by f of x times g of phi, or theta xy, to actually get rid of the g here and get rid of the f here, and instead having f in the denominator here and g in the denominator here. So you get 1 over f of x del square f of x divided by del x squared plus 1 over g of y del square g of y divided by del y squared. The reason why we did this is because I want to keep all the terms which is a function of x on one term, and all the terms which is a function of like all the functions which is a function of y in another term. And let's take this one to the other side of the equation, and you get the following: 1 over f of x del square f of x divided by del x squared. By the way, I can also convert this del's into d's, because I know that the f is only a function of x, so there is no point in like emphasizing that it's a partial derivative, because you cannot take the derivative with respect to y. It's going to be 0 for the f, so it's not a partial derivative anymore. So you don't need to keep y constant. Even if you don't keep the y constant, it doesn't matter. The f is only a function of x. Plus, is equal to minus 1 over g y d squared g y over d y squared. Okay, and here is the point where we need to make an observation. You should observe that this part is a function of x only, right? It's something like h of x, correct? On the other hand, the right-hand side is a function of y only, which is something like maybe, give me a letter, please. Okay, you're not helping me. Let's say s of y. Okay, good. But how can it be true? The left-hand side is a function of x, whereas the right-hand side is a function of y, and they are equal to each other. So how can we actually reconcile these two different things? Any suggestion?
Does it have to be equal to a constant?
Exactly. The only way we can reconcile the two things is we need to equate it to a constant. Cameron, is it you?
No, it's Christina.
Christina. Okay, great. So this is a constant. Excellent point. This must be a constant. Okay. And we know that it matters whether it's a positive or a negative constant. And you can actually try two things. You can say the constant is, let's check, or maybe try. Let's say, is the constant positive or negative. Now, you can actually realize that if you try constant to be positive, you get contradiction. If you, yeah, so let me not go into more detail, but it can be a good exercise for you. Exercise. So please do it yourself, okay? When you find time. So we're going to go with the other possibility, the constant. I mean, I can go over the positive case in the maybe homework help or problem solving session if you remind me, okay? And let's say the constant is negative. So constant must be negative. So let's call it negative lambda squared. Okay, so that's a definitely negative number. So our equations comes out to be let me make it page 3. Okay, so our equations become f, 1 over f of x d square f of x over dx squared is equal to negative lambda squared and 1 over g of y d square gy over dy squared is equal to lambda squared, because this had a negative sign in between, so we make both positive. Okay, so you have two equations. Let's go one by one. Let's start with 1 over f of x d square f of x over dx squared is equal to minus lambda squared. And from here, you find d square f of x over dx squared is equal to minus lambda square f of x. Now, what is the solution to this differential equation? You're taking the derivative of a function twice, and you get like a negative multiple of the same function. Generally, when you take double derivative and if you find some constant times the function itself, it's either the exponential function or the sine or cosine functions. But if you're getting a negative value times the function itself, it's sinusoidal or cosinusoidal. If you are taking the function times a positive number, it's an exponential. You can actually check this really quick. For example, sine of x. The derivative of sine of x is cosine of x, but derivative of cosine of x is negative sine of x. So I get the negative of the original function. Similarly, cosine of x is the derivative negative sine of x, and the negative sine of x is the derivative negative cosine of x. Again, you got the negative of the original function, right? So this is this equation is the reminiscent of this equation. So both sine of x and cosine of x might be solutions. Okay. So it's going to be a combination of the two. So from here, f of x must be equal to c1 times some constant times sine of lambda x. Lambda because when you take the double derivative, you are going to have like 2 lambdas going out, and that's going to actually account for the lambda square. Okay. And that's why we actually like to equate this to like square of some numbers, so that actually we can actually guess the function that solves the equation. Plus c2 times cosine lambda x. Okay. Okay. But here's the thing. Now, here's the thing. We're gonna, okay, so let me do the g of phi as well, and then talk about that. For the g of phi, I'm gonna have 1 over g of phi d squared g of phi over dy squared is equal to lambda squared, and from here we get d squared g of phi over dy squared is equal to lambda squared g of phi. And this time it's going to be an exponential function because you get the same, like you get a positive constant times the same function. So for example, if you have exponential lambda x, the derivative of exponential lambda x is lambda exponential lambda x, and the second derivative will be lambda square exponential lambda x. So you basically get the origin, recover the original function, but with a lambda square constant in front. Similarly, for the exponential minus lambda x, it also solves the equation. The derivative of it is minus lambda exponential minus lambda x. And the second one will be negative lambda times negative lambda, which is positive lambda square exponential negative lambda x. So again, you get the same function multiplied by a positive constant. So either this or this is a solution, or a linear combination of the two are solutions. Okay. Good. So far, so good. So g of phi is going to be equal to, let's call it c1 prime, because it's not necessarily going to be equal to the c1. That's a different function. Exponential lambda lambda y plus c2 prime exponential minus lambda y. Okay. But here's the thing. Now, you have like declared your function to be theta is equal to f of x g of phi, right? And we are not sure about whether the function is separable, right? I mean, maybe theta is not in this form. Maybe theta looks like, for example, xy plus x square y plus 1, right? And if theta is something like this, there is no way you can convert it into this form. But If the theta is like this, of this form, you can convert it into sum of the multiplication of f's and g's. So, long story short, instead of equating theta to f of x, g of y, we should be more careful and write a linear superposition of functions of x times functions of y. And you sum over all the n's. Maybe you can start from negative infinity to positive infinity, maybe from from 0 to positive infinity. We don't know yet, but and you should have some constants here. A, let's call them. Let's call them A, N. Okay. And maybe some of the like most of the ANs are 0, and you just have like one single FNX and GNX. That's still okay. But this is the most general form, because if you want to impose the boundary conditions, your naive f of x, g of y might not actually correctly capture the boundary conditions. Okay. Instead, we're going to assume that the theta is in this form. Now, but whatever we did so far is not trash, because if f of x and g of y solves the equations, then the sum of all those numbers also, or sum of all those functions are also going to solve this equation. So I can use my f of x and g of y in this equation, right? Correct? So I'm going to write down this as fn of x, meaning that the nth function of x, which is going to be still in this form, c1 sine lambda x, but let's call it, we can call it c1n, or, yeah, let's call it c1n plus, sorry. Well, actually, our lambdas might be different, so let's keep in mind that the lambda, we can have the lambda nx plus c2 cosine lambda nx, right? And gny is equal to c1 exponential lambda nth times x plus, this is prime, c2 prime exponential lambda n, so this is y, lambda n y. There you go. Now I should write down my boundary conditions. This is my f, this is my g. Okay. So which boundary conditions do we have? Oopsie. Okay. So we know that the theta at x comma 0 for any x but y is equal to 0 is equal to 0, right? And from here, we should write that f of n at x times g of 0, g of n 0, is equal to 0, right? And from here, you realize the fact that this is this should change with x, but this is a constant number. So you would be so surprised if this f of n is 0. So probably this g of n is 0, right? Because you have a multiplication of two numbers which is equal to 0. So one of them must be 0. Either this one is 0 and or this one is 0, right? But this is a function of x. If this is 0, then actually I'm going to have a trivial solution, and it's not going to make sense. And you're going to see that it's not going to satisfy my general boundary conditions. Okay, so I should have g of n 0, 0. What does it mean? It means that I have a boundary condition for this one, right? If you write it down for g of n 0, you get c1 prime exponential 0 plus c2 prime exponential 0. So you get c1 prime plus c2 prime is equal to 0. Okay, so that's one equation that we have. Now the second one is theta at 0 comma y is equal to 0. And that means f of n 0, g of n y is equal to 0. So this time this constant must be 0. F of n 0 is equal to the f of n was this one, so this thing. So I'm going to plug in 0 there. C1 sine of 0 plus C2 cosine of 0. This is 0. This is 1. So we get, basically we said that f of n is 0. So we should equate this to 0, right? That's equal to C2. So from here we find C2 is 0, right? And what else do we have? We have theta at a comma y is equal to 0. That means f of n at a, g of n at y is equal to 0. From here, since this is the constant number, it must be 0. 0 is equal to f of n a. And from here, we find, since C2 is already 0, we are just going to plug in the C1. C1 sine of lambda a. So from here, what do we find? So that's lambda n a. We know that the C1 cannot be 0, because if it were 0, it would be a trivial solution, because already C2 is 0. So if the C1 is also 0, the f of x would be 0, which would not make sense for our case. It would not be like two-dimensional. So this means that sine of lambda n a is 0. Okay, and there is only like particular numbers that can satisfy this, meaning that since sine is a periodic function and it takes 0 once in a while every after pi, right? The lambda n a must be some multiple of the pi. So lambda n is going to be equal to n pi over a. So you basically not only solve for a general f of x, but you also found out how would the f of n would be discretized, could be written in terms of like integers, which is going to help us sum over these n numbers. Okay. So your f of n should look like the C1 times sine of n pi over a times x. And we don't have the C2 term. Okay. So we found this. We have one more boundary condition to get a better idea about this C1 prime, C2 prime, and so on. But let's do it after like a 10 minutes break. Okay, so I thank everybody for their patience. We've been just talking like for 1 hour. So let's make a 10 minutes break. Okay, if you don't have any questions. Do you have any questions?
Do we need to specify n to be equal to 0, 1, 2, 3, etc.?
Well, this equation suggests to you that the n can be 0, 1, 2, and also can be like negative pi, and so on, and also can be negative 1, negative 2, and so on. So the n basically ranges from negative infinity to positive infinity, right? And it takes integer values. Okay, so it's basically like negative 3, negative 2, negative 1, 0, 1, 2, and so on. So if you sum over n, the n is going to start from negative infinity to positive infinity. Okay? So this is nothing that I make up. It's just what this equation suggests us to take. Okay?